and good morning, everyone. I would like to, you see the title up there, a very long title and a lot of slides, but some of these will go quite quickly. I would like to thank the organizers, Dr. Molly and the rest of these fine folks for inviting us, as well as thank my co-authors, John Zumberg and Stephen Brown, who co-founded Geomark almost 30 years ago. Stephen and I worked on the rock maps that you see, and John is the oil guru, and then we integrated this story together. So again, thank you. So I might as well move on here. And Richard, I want to thank Richard Brito, Dr. Richard, because he set me up nicely for much of this. See if this will actually change my slide.
You're mostly welcome, John.
Thank you. Okay, now it's working. Now it's catching up. Okay, so what we're going to talk about today, what we'd like to visit with you about, is looking at both source rock and produced oil data, and then just a touch of gas data to answer one of the big questions for the Woodford petroleum system that Richard set up, and that is, where did the oil come from, the Woodford sourced oil, and particularly where did it go? So that's the stratigraphic part of this, and this is an ongoing set of studies that we're doing. We're going to first look at the rock set, and you've seen pyrolysis data from Richard, from Emilio, and some of Roger's other students. We have about 3,100 rocks I'm going to show you mapped from about 400 wells. And these, of course, have gone through reasonable QC to make them more real world. And then we're going to move that into further interpret the reservoir occurrences from the Ordovician to Pennsylvanian part of the column, and then the character of these oils, about 330 oils, and then just discuss some very broad postulated large-scale migration pathways that rely on the thermal maturity of the oils, and I'll tell you how we do that. Okay, this is a map. This is a GIS map, and it's a very odd-looking creature, the outline of it. Each of the black dots is a single well, so about 400 wells, again, that were eventually selected. Some of them lay on top of each other if you're trying to count them. And then of the 3,100 samples. So this is present-day TOC. And the two challenges with GIS maps is, one, if you haven't seen them for a while, the areas such up in here, let's see if you can see my pointer. Area up in here have no data, so these are strictly edge effects. Whereas down here, where we have a lot of the information, this nicely parallels Richard's maps of where the production is, of course, because our data are only as good as the production. So this is present day TOC. So if you have 10 samples in a well, you have to average them in order to make a plot. But we know from much work in the peer-reviewed literature, and Dan Jarvie has made some estimations of that you can have a lot of dilution of TOC by the cuttings up and down the section. So it's also instructive to map the maximum TOC that you see in any single well, and that's shown here. So you can see quite a difference, and I know it's small scale, but these last three are 2 to greater than 4, and it'll go up to 10, 12, 15%, maybe 16% TOC. So here are the production fairways, here are the TOC, present day, and TOC max. Now this is for the entire Woodford, and what we have done that we're wrapping up is we have looked at working with some stratigraphers, the lower, middle, and upper Woodford, and so further not really time slice, Roger would get after me on that. We've done these lithologic slices for those various sections to further understand what is where in the Woodford petroleum system from the rock standpoint. So there's other rock eval or pyrolysis parameters we can derive. This wild looking set of colors is the present day hydrogen index. The blue is cool, And that's not good right now because what that means is that it may have started at 500 and now it's at 400. It's these kinds of areas that have much lower present day TOCs, given the same rock quality, of course, that show generation. The production index is just a ratio of the S1 over S1 plus S2 parameters, showing a quick look at where productivity may happen, reaching up to about 0.4, 0.45. The very light areas up in here indicate that the rocks themselves apparently have not produced the fluids that are in the wells, and we have another way to look at that. This is using Dan Jarvie's vitrinite reflectance equivalent based on the Tmax temperature, and the equivalent scale down here that you're used to seeing on the RO scale from Dan's publications. He actually now has a VRE, vitrinite reflectance equivalent temperature 1, his early equation, and now T2, and they're quite similar. And finally, if we want to look at the ground truthing that Brian Cardot has provided through the years, through his career, this is the Woodford taking a look down here greater than 2, where it's really dark, up to 0.5, 0.6, just not quite getting into oil generation in many of these areas. So what I'd like to do is just do a little bit of chemistry here, because I'm going to be talking about biomarkers and isotopes. Just what are these things? So biomarkers are simply hydrocarbons, typically large hydrocarbons, 16, 17, and up into the 20s and low 30s number of carbon atoms. And they occur in some reasonable abundance in nature. They actually occur at the parts per million level. They are stable during diagenesis, and they're molecular fossils or chemical fossils. And we use them like that, as we'll see in a moment. This is an example biomarker, very popular. It's a sterane. It's from a sterol. It's called cholestane. Depending on whether you're a Brit or an American, you say cholestane or cholestane. But there's 27 carbon atoms shown at these different apices, and enough hydrogen to make this a nice saturated molecule. And if you had bacon and eggs for breakfast, you would have been visiting some of the parent material of that sterol, because this is derived from cholesterol. Just a little bit of a reminder on carbon isotopes. 99% of natural occurring carbon on the planet is carbon-12. It has 6 protons, that's what makes it carbon, and 6 neutrons in the nucleus. About 1% naturally occurring has 1 more neutron, and so that's carbon-13. We're going to use that 13-12 ratio as a fingerprint and to follow some natural processes. So on a very simple scale, a methane molecule has about a 99% chance of being carbon-12 and a 1% chance of being carbon-13. You may have heard or recall from early geology classes, if you had them, carbon-14, which has 1 more neutron, still 6 protons, but 1 more neutron, and that makes the nucleus very unhappy, and that decays. So this is how we date Paleolithic campfires and so forth. So we do not have any further interest in carbon-14 in our organic geochemistry world. So with these biomarkers and isotopes, and I'm going to show you some examples, we can get a feeling for a source rock type and depositional environment. Is it a carbonate? Is it a marl? Is it a paralic shale? Is it a distal marine shale, for example? Particularly as we get up into the Cenozoic, we can get a good feeling for the age of the organic matter in those source rocks, because certain microbes, in this case, bacteria, archaea, lived in certain time periods, and they leave behind their metabolic products, and that's what we're measuring in the organic matter. So we can get a feeling for geologic age, particularly as we get into the Cretaceous. Organic maturity is a big thing that we do with biomarkers and isotopes, and I'll illustrate that. We can get a feeling for migration timing by looking at the relative maturities of rocks, gases, and oils. And we get a feeling, and I'll show you some very broad look at this on a good day, migration distance and direction. So let's get back into the Woodford, so nicely set up by Richard. This is a location map of about 330 oils that we used in the study. And these are plotted on top of the USGS provinces. The Anadarko, of course, Sedgwick Basin. So here we are in Canada, Nebraska, the Nebraska Panhandle up by where I live, and down in Oklahoma. Now, it's always instructive to take a look at where the produced oils occur in the geologic section. So here we're going to look at a very large scale look at the stratigraphic distribution of the oils from the Ordovician up into the Pennsylvanian. The significance of this will be outlined a bit later in the talk. And the way you read this chart is, for example, if you take a look at the Cherokee Basin, 83% of the 42 oils that we found in that basin occur in Pennsylvania reservoirs. And in the Sedgwick Basin, for example, 61% of the 38 oils occur in the Mississippian. So this shows the stratigraphic distribution of a number of oil samples that we thoroughly characterized with those biomarkers and isotopes that I just mentioned. Now, this rather colorful diagram is not a stratigraphic column. This is a bit of multivariate statistics, number 1 of 2 that we're going to look at. And this is referred to a dendrogram, and the multivariate approach is cluster analysis. And so cluster analysis will organize oils into groups or families that share similar source rock characteristics using those biomarkers and the carbon isotopes. And this whole thing's called a dendrogram. Each of these little lines is a single oil sample. So you can see how closely they relate, because across the top is a correlation coefficient. And for example, at 0.5% of the correlation on a 100% scale, or 1.0, we end up with 5 major oil families. And members of families 1, 2, 3, and 4, each of these individual oils were most likely sourced from different organofacies of this upper Devonian, lower Mississippian Woodford, the lower, middle, and upper members. However, I draw your attention to family 5, which is down here, which we believe was actually sourced from the Caney down here. And it's kind of interesting to see what the biological world was like in this geologic time, because this composite Fort Worth Basin oil, excuse me, this is a number of oils from the Fort Worth Basin. We see the same thing in the Permian Basin. We can take an oil in the Permian Basin or the Fort Worth, characterize it, and when we throw it into the statistical mix of our Oklahoma, Kansas, Nebraska oils, it plots right here, showing that there's very similar facies between the Barnett and the stratigraphically equivalent Caney. Now, the dendrogram has told us that these oils correlate together to anywhere from 0 to almost 100% correlation of one oil to the other. It doesn't tell us why. So to get the why, we use another multivariate approach, which is principal component analysis. And what this does is going to take, in this case, about 15 different measurements, take all the variability, and instead of making XY plots till the end of time, this will create 3 factor analyses. Factor 1, factor 2, and factor 3 is coming out at the screen at you, which will explain much of the variation in the data. So each of these is a measurement. For example, this is the amount of C27 stearins, and you just saw that cholesterol on an earlier slide. So we take all the pertinent biomarker and isotopic variables derived from the oil samples. The variables are called loadings, and this is where these guys plot. So these colors are actual individual oils key to that dendrogram that we just watched at. And for example, the Caney family 5 oils sitting right out here have very high C27 steranes and very negative carbon isotopes, that is, a lot of carbon-12. So that's how you read these. There are biomarker ratios that are characteristic of different lithophases. For example, carbonate-rich shale facies have a lot of these type of measurements, and carbonate-poor are over here. So you can see that family 1 and 2 Woodford oils over here appear to have been sourced from a more carbonate-rich Woodford facies than families 3 and 4, which are sitting up here in this region. And we can look at this compositional difference and make a decision on what kind of organic matter lived in what kind of facies. So we're talking organofacies here that would have produced these oils. And we do have mixed oils. For example, right here is our oils that have both family 2, but they also have a little family 5 in there. And we can actually rotate these axes in 3 dimensions and see how this all holds together. And over in family 5, the Caney sourced one, there's that composite barnett oil again. So this is what Geomarker refers to as a geochemical summary sheet. You may have seen these in Ken Peters' biomarker guides, Peters and Modowan and so forth. But it's a nice way to take a lot of data and put it together. We have bulk properties. Sarah is very popular right now, saturated aromatic resins and asphaltenes, carbon isotope measurements. This is the whole crude chromatograph of the produced oil as received, or a bitumen extract. And then the steranes, predominantly algal derived, and the terpenes are plotted down here with a number of different ratios. The Woodford kind of stands out pretty easily because it has abundant C29 steranes down here. It has very light carbon isotopes. And then over here, the microbial derived material in the organic matter, these are extended tricyclics. And they are going to tell us a little bit about the depositional environment that this material was deposited in. They're also going to tell us about something called photic zone euxinia that I'll cover in a minute. And that has to do with these guys over here. This is a GC-MS-MS, gas chromatography, mass spectrometry, followed by another mass spectrometer of something called carotenoids. And carotenoids are simply pigments. They're typically yellow, orange, or red. These are the things that make carrot orange, the beta carotene. They make canaries yellow, and they make tomatoes red. But these guys occur in the oils having been generated from the organic matter, and they are also present in the bitumen extracts. It was sort of the intermediate between kerogen to bitumen to expulsion to petroleum. This is beta carotene, again, an orangish pigment. But I draw your attention over here. These guys, paleoreneriatane, and these words are too long for Scrabble. Paleoreneriatane has to do with biomarkers that were created by green sulfur bacteria, and that and isoreneriatane are diagnostic biomarkers for what's going on in the water column. So let me cover that right now. This is a very busy diagram, but what this shows us is that back when John Zumberg and Stephen Brown and I got in the business, the only way you could get really good source rocks were in deep, dark ocean basins, Mordor-like environments. But now we know that the water column itself, through the action of sulfate-reducing bacteria creating H2S and the activity of green sulfur bacteria, can give us indication that the water column was actually euxenic, that is, contained H2S. So everywhere that water impinged on sediments, you had the opportunity to preserve organic matter. Another thing we find in these oil samples, the 300 some samples, is indication of upwelling. If you remember from early geoscience, your early geoscience classes, the west side of continents, the east side of ocean bases are places where, due to the Coriolis effect, you had cold, nutrient-rich waters coming up against the continent. Permian phosphoria up here in the Rockies is a great example of that. And what we see if we look at the oils from the Woodford plotted over here, and these are these tricyclic terpenes versus another set of terpenes, is that carbonate poor source rocks, this pink stuff, Woodford family 4, shows a lot of evidence of upwelling, where the neon family, family 3, has much less of an upwelling signature, and the other two families are intermediate. What this speaks to is the change in the geologic environment, and therefore the change in the types of organic matter that lived in those environments that left behind the organic matter, which when matured gave us this wonderful world-class set of oils. This is a plot of GeoMark petroleum systems, about 150 petroleum systems, thousands of oils here, which provide this calibration. Okay, so let's quickly move through what the oils are going to tell us and the thermal maturity of these. So this is where those 4 Woodford families plot over here. You can see there is a geographic distribution to them. The reservoir occurrence is simply shown here. You can see that family 1 only occurs in Kansas, and the red family down here, family 2, is only in southern Oklahoma. Pennsylvanian reservoirs hold all of the different Woodford families. Again, the Woodford families are related to different organophases. Mississippian reservoirs have some family 2 down here in southern Oklahoma, and they have these interesting patterns. So let's take a look at those patterns and see what we can figure out about migration. The biomarkers we use to define those 4 families that John Zumberg used are all genetic biomarkers. There's another set of biomarkers that are related to thermal maturity. Again, these guys are just hydrocarbons, so they're going to change their character with thermal maturation. So it's possible to take, in this example, 8 different ratios and actually come up with a vitrinite reflectance equivalent based on biomarkers. So these are the 5 families that we've been looking at, the 4 Woodford families and the Caney family that show up here. And this shows the range of estimated maturities. Memoir 110 of AAPG, Zumberg et al., has how to do this if you have biomarker data and how we do this. So what you see is that the Southern Oklahoma family 2 and the Caney source families are the least mature based on our vitrinite reflectance equivalent scale for biomarkers. And really only family 3 and 4 are the ones that are going to be at the correct level for production. So that is quite important, depending if you're getting into your exploration scheme and you're going to put your laterals. You don't want to go in a very immature area. Anecdotally, we know that from about 0.85 to 0.95 is the ideal place to put a lateral, because that gives you enough associated gas to move these fluids, light enough oil from those fluids to move them along the lateral. Now, of course, people make wells in any aspect of this thermal maturity range. So let's quickly look at tying the thermal maturation data for several example families to possible migration pathways. This is the family up in Kansas, Chattanooga family 1. And according to the Kansas Geological Survey, the Chattanooga Shale is stratigraphically equivalent to the Woodford, and we've known that for a long time, covers 2/3 of eastern Kansas, and is especially thick here in McPherson County in this part of the Sedgwick Basin. And we propose that the more carbonate-rich member, perhaps the middle member of the Chattanooga, is the source of the oils. Now, if you take a look at these colors, these are no longer our oil families. These are rather that maturation showing up right here. And what we're going to see is that anecdotally, we know that the very first generated oils from a subsiding source rock tend to migrate the furthest. So you have generation at depth in the source rock kitchen, and you'll have migration because essentially the carrier beds are filled with brine. You haven't had a lot of plating out of asphaltenes and the heavier non-hydrocarbon components of the oils, essentially clogging up the works, and the traps aren't filled. So very early generated oils, again, this is following our sample set of the producing wells, would end up in this way. And if you look down here and look at the scales, these oils are much more mature based on the work we just showed. And again, anecdotally, the first generated oils travel the furthest, and with the subsiding source rock, as it gets hotter and hotter, and different bonds have to break because of the kinetics of this organic matter transferring from carriage into bitumen, and then the bitumen being expelled, even a centimeter or so, becoming petroleum, you are going to get more and more indications of higher thermal maturity in those oils, and they tend to live close to home. So this is one postulated pathway for these family 1 oils.
Excuse me, John. This is Molly.
Yes.
You've got about 3 minutes left.
3, not 5. Holy mackerel.
I didn't want to
Here we go.
interrupt you.
Oh, no problem. No problem. You know, I was a professor for 26 years. Interruption is a fact of life.
Okay.
I'm also a parent and a grandparent, so not a problem. Okay, well, let's take a look at Woodford family 3. These are perhaps from carbonate poor upper Mender, and they also occur in distinct regions, as you can see. We can apply the same logic that the cooler oils are going to be further away from the kitchen. And here you see some postulated migration vectors, actually 2 separate areas. We can then go to family 4 quickly, and you can see the family 4 actually covers the waterfront here. And using the same logic, you can see that the kitchens down here in southern Oklahoma, somewhere in the Anadarko, because this is very broad, and somewhere in the Arkoma would account for the migration pathways that we see. Again, these are postulated, and there are all kinds of questions on whether Woodford oils are in the Nebraska Panhandle and so forth. We have thoughts on that also. We talked about the Caney. It's not a Woodford family. It's by itself. It's Barnett equivalent. But we know it's, and I know Abbas and company and Brian are working on the Caney at great interest. There's a lot of TOC in the Caney. So if we look at the Caney family and family 2, and then some mixed families between 2 and 5, we can see where they occur here. And I know that Alan Hemme, the BNK, chatted about this part of the world yesterday. Gas enters into the picture. We can use gas wetness. This is plotted on Brian Cardot's maturation data to get a feeling for gas maturity. But gas is so mobile, we fold that into the picture a little later. So to conclude, the way forward, what we have left to do to round this study out and to make it, as they say these days, more better, is to take a look at the slices of the lower, middle, and upper Woodford maps. Using that more detailed stratigraphy, then we're going to correlate core extracts, bitumens, and oils from reservoir core from the Woodford source rocks and stratigraphically older and younger source and reservoirs with an expanded produced oil set. Now, Richard set it up nicely looking at the surface of the Hunton, the Sylvan, Viola, because when we did our stratigraphy for the upper, middle, and lower, we also really care about what's below the Woodford and what's above the Woodford in each of these wells. So we're going to fold that in. We're going to take samples that we have that have been collected during the lifetime of wells. Most of you are probably familiar with time-lapse geochemistry, very popular in the Permian Basin, but it can be applied in the scoop stack readily to get information about what is going on through time in individual wells. So we're going to then integrate the rock, bitumen, oil, and produced gas data, much of which you've seen this morning, with the Woodford petroleum system. And we're going to modify that significant question from the first slide, We want to know, where did the oil come from? Where did it go? But we also want to know, at the scale of a lateral, how has that changed through time? So again, thank you for the invitation and thank you for your time.